This is Frank. Frank changed the RTL for one field in one register, and he didn't tell anybody. That caused the software on the chip to stop working, which caused the drone it was controlling to crash into the home of someone who got a bit irritated. We interrupt this commercial to bring you this important message. It has come to our attention that many design teams suffer from non-automatitis or scriptophobia. These have been known to cause headaches and respin regurgitation. If you experience these symptoms, contact Semaphore for a no-obligation checkup. You don't have to suffer. Reach out to Semaphore. We now return to your regularly scheduled commercial.
Okay, so let's go ahead and get started with this session. So if you were expecting Eric Seligman, you've got me instead. Eric had to attend to an issue or a family issue, and so I'm going to be filling in for him. So our first paper is going to be presented by Daeseo. He is the principal engineer of design technology team in Samsung Electronics and is responsible for the company's functional verification methodology development for 20 years in the area of mobile SoC, display, CMOS imaging, sensor, and automotive. He is developing the standard verification infrastructure and deploying it to verification engineers in the company. His engineering experiences are logic simulation, formal verification, and emulation.
Hi everyone, my name is Daeseo. I represent Samsung Electronics in Korea, and my co-workers are Ahyung and Suno. I am going to present metadata-based testbench generation. This is the agenda for my presentation. I will cover the problem we faced and then explain the proposed approach on the concept of metadata-based testbench generation. After that, I will show what metadata we have used. Finally, I will describe two case studies applied testbench generation. One is the testbench for full chip register verification, and the other is the testbench for full chip interconnect verification, and then summarize my presentation. As design size is growing significantly every year, verification complexity is growing exponentially. Due to this increased design size and complexity, we have faced lots of verification challenges. The problems are how to develop verification environment covering the requirement from design, and how to maintain the consistency between design and verification environment, because design changes very frequently during the development cycles. It changes in very late stage also. Generally, the verification for structured one from SoC design, such as register and bus backbone interconnect, need to be done as soon as possible in early design cycle. In case of SoC design, full chip RTL integration is automated using IP exec metadata, but it is not well used in verification compared with design. This is a proposed approach. The most common metadata is IP exec. IEEE 1685 include an information for full chip RTL integration. IP exec consists of two parts. One is IP package that includes port list, interfaces, and registers. And the other is the design architecture that includes IP instances and connection among IPs. However, it is not enough for automating testbench generation because it doesn't have information for security and detailed parameters requiring VIP configurations and so on. So We improved this by extending the contents of metadata. Newly defined metadata contains data for design automation of system IP, such as backbone interconnect and clock and power management unit, and so on. In addition, we added more information for testbench automation, such as controlling sequences into the extended metadata. With this extended metadata, we are able to automate RTL design and testbench generation. This figure shows the proposed full chip register and interconnect testbench generation flow using metadata. vBuilder, internal verification builder, parses metadata such as IPexec, JSON, and YAML coming from design specification and RTL design integration details to populate required information for testbench generation, such as IP address map, registers, location, where masters and slaves are located, interface protocols and signals for masters and slaves from metadata. And then vBuilder renders target project testbench with the existing register testbench template called SFR TV template and interconnect testbench template called bus TV template, which are reusable for all projects. Finally, generated testbench by vBuilder have completed one, consisting of instantiating VIP, connecting VIP port to RTL signals, and generating complete test scenarios. Firstly, we need internal design connectivity information for testbench, and it comes mainly from design specification and IPexec, and it is managed in JSON format. From this figure, for every bus interface in design, this JSON file have a hierarchical instance name like block CPU, AHB2 APB CPU 0. It has interface name AHB00_S, and also it has mode either slave or master, and how it connected with the connection statement. It connected to AHB02 MS interface port in block CPU AHB bridge CPU, and port map for bus signals, detailed connection information for bus signals such as width, direction, bit slices. Metadata holds bus topology information in the figure like this. It comes from design spec, not IPexec. This design spec is also used for bus RTL generation, and it is the complete information for bus backbone. It holds a master list with the hierarchical instance name and slave list having size, base address, interface information, and how they connected in backbone bus. And backbone bus information like AHB bus matrix, how subsequent bus components are connected together. We need project-specific information which is needed for Testbench. In a project, certain address ranges related with specific IP have limitation when generating test scenarios. We have used the YAML format describing this information, and designer prepare this information in this figure. It is a special address map consisting of master, slave, start address, and end address, granularity, write mask, and access patterns. This slide shows how we generate Testbench using metadata. vBuilder has various Testbench templates on IP, subsystem, and full chip Testbench for various applications such as normal function verification, register access verification, backbone interconnect verification. vBuilder renders target Testbench by reading various forms of metadata. In this figure, full chip interconnect Testbench has system Verilog UVM Testbench template written by Jinja template. vBuilder reads project specific metadata information in previous page and then generate target Testbench like this one. This slide shows how Testbench was generated using metadata and how it can be changed easily. This is bus topology in design. BPC ACC underscore 0 APB underscore M3 is an master component replaced with the APB verification IP in Testbench. It is active component, and GPIO CPU APB M4 is a master component using RTL IP. It is passive component. It can be easily configured by sys.csv file, which is generated by vBuilder. By default, interconnect Testbench generates all active masters and slaves. Generally, if a user wants to check the accurate performance using real RTL component, such as DRAM, it needs to be changed easily and regenerate Testbench, satisfying this user intention. One application for automated Testbench generation using metadata is sign-off for IP and SOC design handoff. IP exec and RTL are mandatory deliverables on IP handoff, and it needs to be guaranteed that IP exec and RTL are functionally equivalent. To reinforce this check requirement is added to IP sign-off system, and this check can be done automatically by leveraging register Testbench automation using metadata. IP exec provides the way of describing registers with the various attributes, and they can be modeled using UVM-reg library in UVM Testbench for verifying the functionality of those attributes. For example, write value constraint in IP exec can be mapped with random constraint in Testbench for constraining the generation of random data to registers. To ensure the quality of register access, functional coverage model for register fields are generated automatically using system Verilog macros. And if certain register fields are updated in RTL internally, it needs to be modeled in testable faults in IPexec, and then Testbench awares it by updating this to UVM resource DB. If certain register is read-only, it can be updated to UVM resource DB accordingly. This is a case study for full chip register test bench. Target design is a CMOS image sensor design. As an input, we need 3 metadata files. Top design info JSON file has bus interface information for all masters and slaves. Top bus info JSON file has backbone bus details, and then IPexec catalog file having register, file set, clock, and reset. VBuilder read those 3 files with the option of IPJSON, SVJSON, XLMcat. Also, VBuilder reads one user-specified information, core name, which CPU core need to be used for register read-write operation in full chip. With those information, VBuilder generates complete UVM test bench in the figure in this slide. This slide shows code snippet for generated UVM test bench and result. Generated test bench are register model for all IPs, register model for block and full chip in a hierarchical way. It shows a generalized register access test scenario covering reset check, write and read access using random and specific patterns. As a result, we can reduce the register access test very quickly within half hour with this generated test bench. In detail, test bench generation time takes 2 minutes 49 seconds. RTL compile time takes 30 seconds. And also whole elaboration time takes 30 seconds. And then runtime for generated tests are 13 seconds for 49 IPs. This is a case study for full chip interconnect test bench. Target design is a CMOS image sensor project having 5 AH masters, 12 AHB slaves, and 105 APB slaves. As an input, we need 2 metadata files. Top design info JSON file has bus interface information for all masters and slaves. Top bus info JSON file has backbone bus details. This figure shows the overall flow and command for VBuilder. This slide shows code snippet for generated UVM test bench and result. Generated test bench connect AHB, APB, VIP to DUT bus component on top of RTL component by forcing signals and instantiate VIP. It shows generalized interconnect test scenarios using all masters and slaves. As a result, we can reduce interconnect access test time quickly within half day with this generated test bench. In detail, test bench generation time takes 4 minutes 39 seconds, and RTL compile time takes 3 minutes 18 seconds, and runtime for a generated test is 10 minutes, having 12 iterations with different test scenarios. This is the summary. from the experiment on CMOS image sensor design in this paper, full chip interconnect verification was completed within 2 hours, compared with 1 week in manual Testbench. Also, full chip register verification was completed within 1 hour. With this result, the proposed metadata-based Testbench generation approach is able to reduce Testbench generation time and entire verification time significantly by removing manual process and human errors. In addition, when we apply this approach to big-sized flagship mobile SoC, full chip interconnection verification can be completed within 1 day, compared with 2 to 3 weeks in manual Testbench. As a conclusion, we can completely automate register and interconnect Testbench generation using metadata, and by this automation and metadata, we can also generate various Testbench for different configuration and application, such as power and performance calculation. Thank you for listening for my presentation.
Okay, thank you very much for that excellent paper. So we have a few questions that are coming in. So Daeseo, if you want to unmute your microphone and also enable your video. So the first question is from Cliff Cummings. He says, I have always found IP exact format to be very verbose. Do you generate the IP exact code directly, or do you use a tool to help generate the IP exact representation?
Okay. We have used internal tool to generate IP exec file for packaging IP RTL information, such as register. Also, many system IPs, such as burst interconnect and clock reset management, can also generate IP exec file on the IP creation. From the verification side, there is an internal script which extracts information for verification from IP exec file and store that information to simple JSON format. So this information is used to generate Testbench by verification engineer.
Okay. So the next question is, what advantage does YAML have as a metadata format versus JSON directly?
So traditionally, many verification engineer prefer to YAML file because that is a simple format to store information. So we have used the YAML format for capturing information which is needed by verification engineer.
Okay. So if the question you don't feel is being answered fully, or you have a follow-on, please add it to the chat or chime in. Next question, what language is vBuilder written in?
vBuilder is developed by using Perl language.
Okay, so I assume, is that an internal tool then, or something you purchased?
It is an internal tool.
Okay, vBuilder is, yes, okay. And again, what was the language it was built in?
vBuilder is using vBuilder was developed by using Perl language.
Okay, Okay, so another question, what kinds of additional metadata is needed for verification compared with design metadata?
Okay. Usually verification environment composed of many VIP from EDA vendor or homegrown. So they require more attributes which are necessary for connecting VIP and configuring the VIP functionality. Also, system level information controlling SOC behavior, such as security, backbone bus data routing, address translation, such as interleaving or hashing, are additionally needed for test bench generation. So we try to capture those information to IP exec, and they are used for test bench generation.
Okay. So there was a follow-on question from Jonathan David. He asked the question about what advantage does YAML have as a metadata format versus JSON, which you answered. And then he follow-on question was, so to clarify, you used YAML versus JSON because you already had some experience writing YAML. Is that correct?
Yeah. Yeah, right. YAML and JSON is a similar format.
Okay. Another question from Jonathan David, why Perl? Why did you use Perl instead of Python?
Okay, so VBuilder was developed by a long time ago, more than 10 years ago. So initially, at that time, Perl language is widely used. So we developed VBuilder using Perl language, but we have also planned to renovate VBuilder using Python.
Okay. So next question, how to manage metadata between design and verification?
Okay. Usually, IP developer deliver a proven IP exec file, passing internal sign-off criteria, which I mentioned in this presentation, as a main deliverables. Also, many generatable IP, such as bus or system control IP, generate IP exec file. All these IP exec files are gathered to our central IP management data system and consumed by SOC integration team. On top of IP exec, SOC team assemble SOC design automatically and generate SOC level metadata and release these to version control system every regular RTL release. And then verification team consume metadata downloaded from version control system. Thus, we can manage metadata consistently between design and verification side.
Okay. So we have one last question before I think we're out of time. So the question is from Bill Moore. So how rich are your metadata files? Approximately how many keywords did you define? For example, interfaces, mode, connection, or port map?
Yeah, we have variable. We have many metadata keyword which captured in our design IPJ metadata file.
Okay. Does that answer your question, Bill? Okay. Doesn't. So are you thinking you've got like dozens of these in your files?
I think so. So yeah, dozens of IPv6 keywords. So sometimes we extended some information using vendor extension. So that is not a standard one, but that information is needed for our internal test bench generation and also our other automation tool.
Okay, great. Okay, so I think we're going to need to end it here and move on to the next paper. So thank you, Daeseo, for the excellent presentation. Again, don't forget to rate the presentations for the Best Paper Award. And we'll go ahead and move on to the next paper. So the next paper is entitled Automatic Translation of Natural Language to System Verilog Assertions. It'll be presented by Abhishek Chauhan. He is a senior machine learning engineer at Agnisys Technology. He's involved in the development of their products like iSpec.ai, automatic test sequences from English text-based specifications, etc., to ease the flow of SoC IP development with the use of artificial intelligence and machine learning. He is passionate for automation of existing work in the industry and has explored ways to use machine learning in complex digital verification, regression validation, and also simplifying the use of SVAs, etc., in a CI/CD cycle.
This is Frank. Frank changed.
Hello everyone, my name is Abhishek Chauhan and I am a senior machine learning engineer at Agnisys. I am here to present a work in the paper with the title Automatic Translation of Natural Language to System Verilog Assertions. So let's start with the presentation. As we all know, verification and validation of design is a complex and time-consuming process. It requires a lot of manual work. There is so much need to automate in this, and hence machine learning can be used to great extent for automation in this regard. Now let's move on to the system Verilog assertions in design verification and validation. System Verilog assertions are primarily used to validate the behavior of design against its specification. It provides information on functional coverage of the design. It is also used as a formal specification language, making the requirements clear and unambiguous to automate validation of design against the specification. These are some important points about system Verilog assertions. So let's talk about some complexities in system Verilog assertions. We all know writing SVA requires an expertise and context knowledge. So it is a difficult task to write an accurate yet compact SVA. Often dedicated verification engineers write SVAs that deviate from the actual intended assertion. That would ultimately lead to missed design bugs and lower functional coverage. Starting with our objectives, which are A, to solve the problem of writing sophisticated system Verilog assertions through machine learning. B, to bridge the gap for verification engineer who do not have any prior knowledge of writing SVA to functionally validate the design. C, and also to create the pipeline to understand the user's natural language description of assertions and generate SVA, vice versa. And D, at the same time, to help users to conceptualize their intended assertions into an actual SVA. Let's focus on the machine learning part that we have used some deep learning techniques like transformer neural network. The transformer neural network aims to solve machine translation tasks while handling long-range dependencies with ease. Earlier, recurrent neural networks were used for the machine translation task, but they had their limitations like no parallelization, not able to learn long-range dependencies, and were very slow as the data processed sequentially. Presently, it is the state-of-the-art network in NLP, which is natural language processing, and thus outperforming for all NLP datasets like Squad, Babel, etc. It has an encoder-decoder with self-attention based architecture, and it is being used in computer vision applications also. It has shown much more promising results as compared to previous neural nets like recurrent neural network, and we have used it to perform both machine translation and name entity recognition tasks. This is an image of the transformer neural network. Let's see how this network works. You can see both encoder and decoder block marked by dotted lines. The encoder is on the left and the decoder is on the right. Both encoder and decoder are composed of multiple such modules described by NX in the figure, and the NX here is n times, which is a hyperparameter for the model. Within them there are other blocks or layers, and the source language or inputs and the target language are first embedded into an n-dimensional space using embedding layer, and we cannot use strings directly here. The embedding layer helps in learning the representation of token in vector space and collecting their contextual information in that space. Then there is positional encoding. It is a very relevant information for translation and helps in giving word or part in a sequence a relative position, since sequence depends on the order of its token. Thus, the positions are added to the embedded representation of each word. Now, there are other blocks like multi-head attention layer, as it also plays crucial calculation for the task. I will not go deep into calculations, but the transformer used the concept of multi-head attention, and the layer basically score each word of the input sequence against the every word of that sequence. The score of each word determines how much focus to place on other parts of the sequence as the model encode a word at certain position. Then there are other blocks. One of them is add and norm layer. Add here refers to a residual connection that adds the input of each layer to the output of that layer. And norm here means the normalization, and also one of the many computational tricks to make model training easier and hence reducing the training time and increasing the model performance. And the FFN block here is feed forward neural layer, and it creates a new representation based on the information from self-attention layer. Now in similar fashion, decoder works. Decoders share the same property as they are also very similar. You can see decoder also have the same layers, but between them is an attention layer that helps decoder focus on the relevant parts of the encoder input, which is an input sentence. There is also masked head attention. This step involves special masking, which is necessary for the training. And there is an output layer, FC layer, which is fully connected, or we can also call it dense layer. It helps in scoring each word in target dictionary using softmax, and then using greedy approach, choosing the word with maximum score. That is all about model architecture. Then there is tokenizers. It is a method of converting text data or sentences into multiple tokens or subwords, and then again converting to numerical values by mapping the ID of the token using dictionary. Due to lesser availability of data, it was difficult to build a good tokenizer. So we took a pre-trained tokenizer that also capable of dealing with out of vocabulary words. Along with it, we also took associated pre-trained embeddings that were initially trained on English corpora dataset using similar network. And the following tokenizer excludes multiple spaces and consider punctuation as separate token even if they occur together with no space. We have invested a lot of time in data mining. It involves collection of domain-specific cases. The information available was very limited related to system Verilog assertions. So we considered multiple sources for samples and to focus more on SVA practices. We created data generators using Python scripts that involve complex mapping of rules adhered to the rules of target language. Data was also generated using phrase-based dictionary. These are the steps done to build an initial model, and then the idea was to generalize it further using augmentation techniques and fine-tuning dataset. To generalize it further, more data was required apart from collected samples. We only depend upon augmentation techniques to generate more samples. The data needed to be monitored in order to avoid distortion during augmentation, and also involve training the model with fine-tuned dataset to remove data uncertainties. During dataset building, we observed large number of inconsistencies. We also observed large number of overlapped meanings, and training with such data is bad for model as it will not converge. And debugging of such cases were laborious and time consuming. It was also found that parallel meaning didn't exist between the data samples, unlike other cases such as German to English or vice versa. So these were some data inconsistencies that we faced during dataset building. Now about the model training. So the model was well trained with a batch size of 64 and a maximum sentence length of 512, and trained for about 50 epochs with 300 batches each. Model was able to learn quickly even the complex scenarios. The training was data-centric due to the absence of generalized dataset and was expected to overfit. So to increase model generalization and decrease models overfitting to present dataset, we depend upon augmentation of that data. So we observed improvement in performance using augmented samples, but the data needed to be monitored to avoid distorted samples. Augmentation was performed at both word and character level, and the mechanisms were: first, the back translation. As you can see a table in the slide, it is an example of back translation. Let's see row 1. So there is a sentence which is signal A is high and go low in the next cycle. And it is translated to another other language, say French for now. Then it is again translated back to its original language. You will see that some part of the sentence has been changed, which is signal A is high and decreases in the next cycle. So that is how back translation works. And the other one where signal A changes to 1, which has been converted by same function into the signal A goes to 1. So that is how it works. And then there are others like random word or character swap, where random word or character are swapped in the sequence. Random word or character deletions, where random word or character are deleted from the sequence. Random word or character insertions, where random word or character are inserted in the sequence. And the synonyms replacement, which is words with same meaning were exchanged. The model has some hyperparameters, and that are number of layer, attention adds, embedding size, and we have tried few of these combinations, but the above mentioned numbers are found to be working best in our scenario. We saw increasing number of layers lead to increase of model training time as well as model convergence time. Increasing embedding size led to fluctuation of the accuracy, and also model jumps from one point to another. Now let's move on to the next slide. These are some data samples with predictions, and I will now explain some of these samples. Let's see row 2 for now, which is X is stable, rack is low after P ready is unknown. After 2 cycles, AR ready is low. So it is translated to an actual SVA. And you can see all the signals are identified correctly, like ACK, rack, P ready, and AR ready. These are some signal names chosen randomly. You will see model was able to predict correct ordering and also was able to learn relationship between the signals as well. Let's focus on a part of the sequence, which is rack is low after P ready is unknown. So you will notice from the output sentence that P ready has come before rack. So here we observed the model was able to learn the restructuring of the output sentence. And now let's see the next one, which is after a 5 valid signal A goes high until signal L arrives. As per the predicted output, the model was able to distinguish signal A at 2 positions correctly and also able to generate new things. Now let's see the next one, which is whenever signal A goes high, signal B must go high within 2 clocks and go low in the next clock. So here model was able to translate the phrase within 2 clocks correctly, which is ## 1 to 2 clocks in the output sequence. And let's see the other part where signal B is referred again in the next sentence, and the same has been translated correctly in the output sentence. And here model was able to learn the references also. Now let's see another one, which is the signal A is not equal to signal D for 10 or more non-consecutive clock cycle. So here we can say that the model was able to learn the expression correctly and generate it as well. And now let's see the next one, which is signal A rose to 1. Here the model was able to generate the property correctly. And in the next one, signal A is high and go low in the next cycle. Here you can see the signal A has been referred again in the sentence, and you can also notice the model was able to generate signal A correctly at both positions. Now coming to third last. For this, I want to add that we adhere to some rules for some SVA syntaxes, and we are presently collecting data samples using online tool and from other sources. So here is an example for it, like the sequence in which signal A is high and signal D is low, and the sequence in which signal C is stable and in the next cycle signal E is low. You can see model was able to point out both sequences and used AND sequence operator to join them. And similarly in the next one, where the sequence in which signal A is high and signal D is low, and the sequence in which signal C is stable and in the next cycle signal is low, they must end at same clock cycle. So here you can see model was able to learn long range dependency and predicts the correct syntax. You can see both sequences are joined together using intersect sequence operator, as both must end at the same cycle. So let's see the next one, which is when signal A is high and in the same cycle signal C is less than the value of signal D before 2 clock ticks and must occur within the sequence signal A is high. So here you can see the model was able to convert it to a actual SVA expression, and these were some data samples and model capabilities. About the results, if we summarize our results from the experiment, It resulted in a state-of-the-art for machine translation. It has achieved a greater accuracy. Model was able to learn and translate complex descriptions of assertions. It has also achieved an accuracy of around 99% on training dataset and achieved an accuracy of around 83 to 85% on an internal test dataset. Coming to the actual application and its usage, like it will help verification and validation engineers to easily capture accurate SVAs through their specification level descriptions, automatically hooking assertions from descriptions to the design for improved functional coverage. And the following application has been already deployed on iSpec.ai. And we will highly appreciate if anyone wants to try the model and give us some feedbacks. There are few roadmaps for us to cover in this, like covering more complex scenarios, increasing model reliability, improving generation of sophisticated SVAs efficiently, and also covering and understanding users' natural language intent. These are some references. Anyone can refer to them for more information.
Okay, so Abhishek, if you could unmute and turn on your video if you have it available, we'll answer some questions. So from Cliff Cummings, this looks like an interesting tool to generate SVA. Is this an internal tool only, or is there an available commercial version of the tool?
Yes. The tool is available online and it is at iSpec.ai. And basically, we are continuously learning and correcting the model with the feedback we receive from this beta version at iSpec.ai. So I will highly appreciate if you give it a try and provide some feedbacks.
Okay. The next question, very interesting idea. Is there any study done on the ratio of false positives and true negatives with respect to successful predictions from the model?
Yes, we did a good study about it. I also referred to a system Verilog reference manual to make data samples. And as far as for the model's accuracy, like we have created a test suite that help us in deciding the behavior of the model and also the direction in which the model is going. And we have also added some fake samples or augmented samples, which also tell us the not suitable behavior of the model. So that is how we released a version, seeing the samples from the test suite.
All right.
Yes.
So another question from Cliff. So this is referring to the sum data samples slide. In the example, it says the signal A is not equal to signal D for 10 or more not consecutive clock cycles. And then it produced an assertion. It was signal A not equal to signal D, and then a 10 colon $. So is there any warning produced about how this assertion can significantly impact simulation performance? Using $sign to eventually find a signal can be quite costly, and we might not want to make it easy to create the $sign assertions.
Yes, about that, I would like to add that I haven't studied the SVA assertions in this depth. So what I'll do, let's take it offline and I'll get back to you with the answer later.
Okay. So, Greg, if you give me a minute, so I'll add on behalf of Abhishek. Yeah. So coming to this question, so Cliff, so what we focus now in this beta version of the release tool is basically just to translate the description into SVAs, so we get the correct SVAs. I know you're talking about whether to send out warnings regarding the time frame. So that that we have as of now, we haven't added in the future scope, but we'll definitely add it. So it's a good suggestion. But in the beta version that we have released right now, we are just focusing on to capture the description and convert them into actual correctly indented SVAs. Yeah.
All right. The next question is from Tim Schneider. Can you elaborate on the amount of training time required for the model?
Yes, it took around a day to train this model as the data was limited as for now. But there are some data uncertainties, and if we want to correct those data uncertainties, so the training time can be increased.
Okay.
So it took us around 50 epochs and like 600 batches in each epochs. That much amount to help us in training our model quite good.
Next question from Bill Moore. Does it work in reverse? Can you convert SVA into natural language?
Yes, the reverse model also exists. We have prepared a separate model for it, and it is also available on ispec.ai. You can also check it out there.
Okay. And then a question from Sarmad Paracha. Kindly, can you mention the specificity of the model?
I do not get what you mean by specificity.
Okay. Sarmad, can you add a little more detail what you're looking for here? Perhaps they already have. So next question from Sarmad is, I'm interested to know that on which domain of designs your model is working. Does it work for computer processors, bus protocols, medical, or image signal processors?
Yeah, so Asif, can you jump in and see?
Yes. So Sarmad, as of now, the data sheet that we have referred to, the industry standard data sheets and the feedback, the input from the experts and our own internal data set, those are all based on bus protocols and the actual searches on computer processors as well, but not on medical or signal processing. So since Abhishek has told you we have a limited data set on actual SVAs, we also try to replicate those data in the model to generate large data sets for the training part. So yeah, it's limited as of now, but yeah, we'll surely improve. Thanks for the feedback. Yeah.
Okay. Another question from Bill Moore. Is the SVA output guaranteed to be syntactically correct, even if the semantics might be off?
As of now, I will say that the SVA output may or may not be correct synthetically. But we are in a stage of continuous learning and correcting the model, and we are also getting feedbacks we received from our beta tool also. And we have also doing some internal creation of samples so I'll hope the model a user can get accurate and synthetic SVA in future.
Okay.
Yes.
So
yes.
Go ahead.
So yes, Greg, sorry to interrupt, just to add.
No problem.
So as Abhishek mentioned, what we have achieved now is that we have our internal test data for assertions and their actual description and their assertions that we use in our internal tools. So we have cross-matched with those, and we have found the accuracy of the model as of now on those data set to be 83 to 85%. Yeah.
Okay, great.
So yeah, that's a reference point for results right now.
All right. So let's go ahead and move on to the next paper. The next paper is entitled A Comparative Study of Chisel and System Verilog Based on Logical Equivalent Swerve EL2 RISC-V core. It'll be presented by Waleed bin Ehsan. He has led the team behind the development of the Quasar project. He has worked on all facets of SoC design from spec to GDS2. He is currently working as an RTL design engineer at a startup to develop high-performance RISC cores. He has worked at Lampro Mellon as a team lead for multiple teams from verification to design, and his passion lies primarily in design. So with
Hello. Hi, everyone. My name is Waleed bin Ehsan, and I'll be presenting our paper, a comparative study of chisel and system Verilog based on logical equivalence, Swerve VL2, RISC-V code. So the overall presentation will be like this. First and foremost, we'll go over the introduction of the whole paper. Then we'll look into the microarchitecture of the design that we implemented. In our case, that is Quasar core, which is a chisel implementation of Swerve VL2. As you know, Swerve VL2 is an open source core by Western Digital. And then we'll move toward the methodology of this paper. So what methodology that we adopted, especially for the verification side. And then we'll look into details into the results that we calculated of a comparative analysis between chisel and system Verilog. And those comparative analyses were done on Quasar core as well as Swerve VL2 core. And finally, we'll look into useful links. As you know that Swerve VL2 is an open source course, as well as Quasar is an open source core. So all of the results, data, and the code base can be found at these GitHub links. Let's move to the introduction of the paper. So we actually wanted to do a comparative analysis between chisel and system Verilog. For that, we opted to choose a design that is well known in the industry, which is Swerve VL2. So Swerve VL2 is a 4-stage, mostly in-ordered pipeline core, which is open sourced by Western Digital, and it's based on RISC-V ISA. So Swerve also supports RV32 IMC instruction set. So the logical equivalent chisel implementation for the Swerve core is called Quasar. And after making both of these implementation logically equivalent to each other, to calculate majority of the results, following 4 key parameters were calculated. First one was maximum frequency, or the effective maximum frequency at a targeted frequency. Then the silicon area, and the dynamic power which that silicon area consumed. And finally, there were some qualitative results such as code readability and code maintenance. So let's dive deep into the microarchitecture of Quasar. So Quasar is a 4-stage, mostly in-ordered pipeline core that supports RV32 instruction set. So block diagram of this core is shown. So the 4 stages of Quasar are IFU, decode, execution, and LSU. So the LSU actually starts to operate in the decode stage itself, but it takes 2 stages. That's why the whole core is a 4-staged core. And majority of this code base is very much parameterized to have different branch predictor size, store buffer size, bus buffer size, And you can actually configure this whole core whether to operate on AXI or AHB. It also have configuration that can enable or disable iCache, ICCM, or DCCM, or all three of them. It also have a RISC-V compliant debug, a PIC controller in it, and there are basically four channels of the AXI or AHB depending upon your configuration. Firstly, for the IFU, where all of the iCache misses or the instruction misses are taken care of. There is the LSU side AXI protocol or the AHB protocol that actually tends to external load and store. And finally, there is the debug AXI protocol as well as a DMA port, which act as a slave when a DMA is writing to a memory. So as I said that this is an mostly in order core, which what I mean by that, for example, we can actually have a bus buffer of different width. If there is an external load, basically external load, then that bus buffer location gets allocated. As long as there is no dependency upon that load value, we can keep on getting the instructions into the decode as well as in the execution pipe or the LSU pipe. What it becomes is that wherever there is some this sort of a scenario, or if there is a divide instruction, so basically the core goes a bit out of order, but it doesn't have an ROB, so it basically doesn't support an imprecise exception. So whenever there is an imprecise exception, it just restarts the whole core. So that's basically the microarchitecture of the Quasar core itself. Then the methodology. For the methodology, we basically had four key parts that we divided the methodology into. First and foremost was that as the code base for SWRVL2 is an open source code base. So for that, and there is no microarchitecture spec from the Western Digital that was open source. So first and foremost was to comprehend the microarchitecture of SWRVL2. And this led to the compilation of a microarchitecture spec document in the internal, for the internal Quasar design. This microarchitecture spec was then passed to the design team, which actually implemented the whole core and chisel. Then the time came for verification. So for verification, basically the whole verification methodology is consistent of two phases. First was co-simulation, and secondly was like, if we did verification of Quasar with the traditional methods, then we had to make it functionally equivalent to SWRVL2 to make a comparison that would be justifiable and non-biased. What we concluded from this is that this would in turn take quite a lot of strain on the time to completion of the whole project. So it was evaluated better to do an RTL to RTL leg on both of those implementation, just to increase time to completion. And for leg to actually work, we actually needed a basic level verification. So for that verification, for that basic verification, a co-simulation environment was made where both of the cores actually get instantiated into a same environment with same ELF and all of those parameters, and majority of the signals were hooked and checked that they were operating similarly. So for the leg, the golden reference model that we used was SWIR VL2, and the implemented design in this LEC was our Quasar core. Let's look into the methodology verification a bit deeper. So as I said that it was evaluated that in order to increase code coverage beyond 90%, we actually had to do much work was needed for this, and it was evaluated that it would be quite a huge toll on the design time itself. So for that, we actually moved toward LEC. But before LEC, we had to make the code base solid enough so that a LEC can be performed on it. For that, a co-simulation environment was made. As you can see in this figure, the co-simulation environment that we made was the SWIR core was running in the same environment parallel to a chisel generated RTL version of SWIR core Quasar, and majority of the signals from the IFU block, from the decode block, from the execution block, from the LSU block were hooked, and post simulation all of these logs that were made during simulation were compared, and if that comparison actually do pass, then the co-simulation flagged us that it actually passed. Instead, if it failed, it actually tells you where the actual failure occurs. So in the co-simulation, each of the parameters for both of those implementation was same, meaning they basically had the same ELF, same clock frequencies, and all of those parameters were same, just to make the comparison a bit less, more unbiased, as to say. And for the LEC, what we actually used formality tool to do LEC, and the LEC on both of those implementation was done in a hierarchical manner. What I mean by that hierarchical manner, I basically we actually made the lower blocks logically equivalent to each other from the reference design. After that, the upper blocks were made logically equivalent, and finally the whole core was made logically equivalent to the other one. So one thing that bothered us quite a lot is that Chisel actually renames signals quite a lot. So for that, we actually had to do quite a lot of user matches, and those user matches racked up to be around 15,000 or more user matches, just to make both of these implementation logically equivalent to it. So after making the core, both of these implementation, one being SWIR and the other being Quasar, logically equivalent to each other, the next step was actually to calculate these different parameters. So in order to calculate all of our results, we actually used Skywater 130 nanometer PDK. In this PDK, both of the implementation were subjected to a frequency sweep, and after that frequency sweep, four major parameters were analyzed, namely the maximum or the effective frequency, the silicon area, the dynamic power, and finally the qualitative results such as code readability and code maintenance, which included the number of lines of code actually written for both of those implementation, and actually how easier or hard it is to comprehend the code base itself. So let's move towards the frequency. So for the frequency, the results that we accumulated are shown in this and in our paper as well. So as you can see from this, that the effective frequency for SWIR was around 145 megahertz on a 180 nanometer technology node, whereas for Quasar it was around 141 megahertz on the same technology node, but on a different targeted frequency. So from these results, we can evaluate that SWR-VL2 is about 2.7% better in terms of frequency relative to that of Quasar. Let's move towards the next result. So in terms of silicon area actually used on the same targeted frequency where the maximum frequency was achieved, these results were calculated, and it was found that the area of Quasar is about 4.2% smaller relative to that area of SWR-VL2. And finally, the power. So on account of dynamic power, it was evaluated on the same targeted frequency that Quasar is about 3.8% better in terms of maximum operating so Quasar is about 3.8% better in terms of power at the maximum operating frequency relative to that of the SWR-VL2. And finally, the qualitative results, such as the number of lines of code and the readability of code. So this actually is where Chisel shines. Is in Chisel, you actually need much less number of lines of code to describe a whole design, because majority of the design that you are doing can be described in a higher abstraction level, and basically Fertile take care of converting that higher abstraction level to a lower abstraction level, and finally generating Verilog. So for the number of lines of code that we actually wrote for Quasar, they were around 12,000 or so, and for the SWR, there were about 18,000 or so number of lines of code. This is taking out all of those comments and the memory blocks. So from that, we actually evaluated that the code base for Quasar is about 45 to 35 to 40% as less as compared to SWR-VL2, and that actually increases the design time as well, because you actually need to write lesser number of lines of code. For the readability of code, can actually be subdivided into two parts. One being the readability of the Chisel or the Scala written itself, and finally the other one could be the readability of Verilog generated from Chisel or Fertile. So the readability of Chisel itself, so we evaluated that for a person who is much well versed in Chisel itself, it is assumed that the readability of Chisel code is much easier as compared to that of system Verilog one. The reason being that as the code base is written at a higher abstraction level, it is much easier to comprehend the whole microarchitecture as compared to that written in a system Verilog based or a lower hardware description language based environment. But for the readability of Verilog itself, as I just mentioned in my prior slides, that we actually had to do more than 15,000 user matches. So what Chisel actually does is that when it generates Verilog, it actually renames quite a lot of signals, and those signals actually tend to become quite hectic in order to debug or to understand. So the readability of generated Verilog itself is quite tedious as compared to in a system Verilog based code base. So we concluded that the readability of generated Verilog itself is quite hard to understand in terms of a code base that is written in this system Verilog environment itself. So this concludes our all of those results that we actually formulated. For the conclusion, what we concluded from all of this is that the PPA-wise, both of those implementation had their peaks and drops. So overall, we think PPA-wise, both of the implementation are relatively equal to one another. But there is actually a problem that Chisel community is facing because majority of the tools used in an industrial environment all uses system Verilog or Verilog as its baseline. So in order to Chisel to thrive into industry itself, there needs to be quite a lot of work to be done on the EDA tools itself to provide support for Chisel itself, or the other way around could be that all of this verification, all of the verification stuff, if somehow Chisel can incorporate all of those things that an EDA tool does in Scala itself, or to build an environment around it, this bottleneck can be overcome. But in terms of qualitative results, we concluded that Chisel actually performs well as compared to System Verilog. The reason being that the design time or the time to market can be reduced using a Chisel-based environment. So as I said that both of these core are open sourced. So the whole code base for Quasar core is open sourced and it can be found at this link. The authors of this paper actually wrote a Chisel training manual, and that training manual is also open sourced. This training manual actually goes from the very basic level concepts of Chisel to the very high level concepts of Chisel. So a person can quite easily get started with Chisel using this manual. It is also open source. If somebody wants to look at it, feel free, because it's basically open source and all. So thank you very much for your time, and I would love to answer all of your questions.
All right, Sab, Abhishek, if you could please unmute your microphone and turn on your video. So some questions have come in. So on the verification co-simulation slide, how much post-processing had to be done on each co-simulation log file to successfully be able to run the comparison?
Yeah, so thanks, Cliff, for asking this. So there was not much post-processing that was needed to be done. The reason being that both of these implementations were running in the same environment. So basically they had sort of the same displays for all of those signals. So none, little to none post-processing was done for this comparison to start running. We actually did need to wait for the simulation to end. After that, there was not much post-processing that was required.
Okay, the next question is from Andrew Parker. If you didn't have to do hierarchical LEC, could the Chisel model have been better? For example, more abstraction, resulting in better performance or power, etc.
Yeah, so the performance and area and power doesn't actually depend upon LEC itself, because at the end of the day, you actually do need to have all of those hardwares in order to do the actual work itself. So even if we did in a non-hierarchical manner, we'll still get the same performance numbers.
Okay, so I was just curious if were you able to successfully complete LEC? I mean, the two were logically equivalent.
Yeah, so the baseline configuration for both of these implementation, we were actually able to get the whole core both the implemented code fully like clean.
Okay.
Though we had to do quite a lot of. Yeah, go ahead.
Yeah, so if the two were logically equivalent, why was there even a need to go to functional verification?
Yeah, that's why we actually didn't go to functional verification. We actually evaluated whether to go from the left route or the functional verification route. And if we opted to go from the functional verification route, so there can be this comparison could have been a bit biased, because there can be a probability that first of all, this project would have taken quite a long time as compared to the LEC route. So we actually had a constraint on the time to completion for this project. So we opted to go the LEC route.
Okay. Another question from Cliff. I have heard about Chisel, but I was hoping to see a few side-by-side comparisons between Chisel and System Verilog code. Can you give us a quick description about the origin of Chisel and how it is supposed to be useful in RTL design?
Yeah, so sorry, Cliff, to disappoint you because not having those comparison slides. But yeah, so basically, Chisel originated from the fact that people thought that it's going to be a better idea to write all of these RTL in a higher description language. So if we write it in a higher description language, the majority of the work that actually needed to be done was either from the synthesizer or from that block that actually converts this higher abstraction language into a lower level Verilog similar language. So that conversion is actually being done with a tool called Fertile. So Fertile actually takes the Chisel, he unrolls it accordingly and generates Verilog. So the major things you can see in Chisel and System Verilog would be that you can actually write quite a lot of code as if you were writing some sort of a software itself. So people can actually write their own modules and plug them in as a library, and you can actually use methods from that library, and it's going to generate that module itself. So that's why we were able to reduce that number of lines of code.
Okay, the next question is from Jonathan David. Does the Chisel language support models of analog blocks? Are there any Chisel simulators? And if there are, do they support simulation of those analog blocks?
Yeah, so to the best of my knowledge, I know that Chisel currently don't have much of an analog blocks in it. Usually the analogs block that we used to work on were so the verification was majorly done in generated Verilog, and then we connected those generated Verilog with the analog block. So yeah, but not completely sure that Chisel have an analog simulator. I'll have to look it up and get back to you on this.
Does Chisel have a digital simulator?
It kind of sort of have a digital simulator built in itself, but that digital simulator, people use it, but we actually didn't use it because the problem still can be that you actually use that digital simulator, and for some reason, Fertile actually does some sort of an error, and the generated Verilog is not according to that Chisel itself. So it's always a better option to run your simulation in the generated Verilog until you have a tool that can actually do some sort of a logical equivalence check between the Chisel itself and the generated Verilog itself. So if that sort of a tool is available, then that whole verification can be done in Chisel itself.
Okay, so the last question is from Juan Santana. So just real quickly, the benchmarks you gave for frequency, dynamic power, were they ran directly on the Chisel description, or did you have to synthesize down to RTL to get those benchmarks?
So yeah, for those results, we actually needed to synthesize down to RTL, and after that, we calculated both of those results in design compiler.
Okay, fantastic. All right, so let's go ahead and move on to the next presentation. So before we finish or go on to the last presentation, again, I encourage you to rate the presentations for the Best Paper Award and also to visit the virtual exhibit hall. So the last paper is entitled Flattening the UVM Learning Curve, Automated Solutions for DSP Filter Verification. It's presented by Avinash Lakshminarayana. Apologies if I butchered that. He is a design engineer manager at Silicon Labs. He has more than 10 years of experience in design verification and has worked extensively on UVM, formal verification, and other advanced methodologies at both the subsystem and SoC level. His areas of interest include low power designs and radio and DSP subsystems in the IoT space. Previously, Avinash worked at ARM on low power interfaces and AMBA 5 protocol verification. He has authored multiple IEEE papers on power estimation and coprocessor design, space exploration for FPGAs, earned a master's degree of science in electrical engineering from Virginia Tech. Thesis work has been published in the book Low Power Design with High Level Power Estimation and Power Aware Synthesis.
Hi, my name is Avinash Lakshminarayana, and I'm a design engineering manager at Silicon Labs. My team focuses on advanced methodologies for IP and subsystem verification in IoT space. DSP filters are one of the key components in our radio subsystem. When it comes to verification, there are some unique requirements and constraints to the DSP blocks. It was natural for us to collaborate with MathWorks to solve some of these issues and develop a robust verification solution. This was because the systems team already performs design space exploration and modeling in the MATLAB environment, and our golden reference models for RTL development are also in MATLAB. The intended audience for this presentation is DV engineers looking for a light UVM framework that verifies DSP filters with complex data paths but simple control logic. The digital filters are used to perform a series of mathematical operations on digital signals. The primary goal is to transmit and receive signals efficiently and with minimum distortion. Typically, the system team evaluates, develops, and tunes the entire filter chain in a MATLAB environment. Then, an RTL designer breaks the model into smaller components and implements them in System Verilog or VHDL. The systems team also provides a few golden test vectors in a text file format. These golden vectors are supposed to represent real-world use cases. The verification engineer uses these test vectors to compare against the RTL implementation. As the designs get more complex, we increasingly find a need to run the MATLAB model with new input vectors and compare the results against the RTL implementation. Such vectors may be meaningless in the context of a full system, but they will help with initial debug. For example, an input vector with all zeros might expose some basic connectivity problems. Sometimes a constrained random input pattern may also unearth a corner case bug in the RTL design. Running MATLAB models from within the test bench gives us a stronger ability to control the stimulus and improve the overall test bench. Traditionally, we used simple test benches with C, System Verilog, or even scripting languages to verify DSP blocks at unit level. That paradigm is now changing. Clock gating, interrupts, and even FIFO-based coprocessor structures are becoming common. This is accelerating the DSP test benches towards advanced verification methodologies. That brings us to the secondary goal of our paper, the UVM deployment. In our improved flow, as we show in this paper, the MATLAB model is an input to the test bench and not just for RTL development. Through the MATLAB stimulus library, we can reuse a previously developed stimulus source or even create new stimulus sources if needed. Because the flow is fully automated, scope for TB bugs are limited once the flow is mature. This further contributes to the overall efficiency improvement. This picture shows the radio subsystem of a typical IoT chip. The DSP filter IPs we are interested in is shown at the bottom right corner of the slide. A narrow time to market in the IoT space means that bug escapes can be quite costly. At the same time, a quick bring up and lean test bench gain precedence over complex environments with long design and maintenance cycles. In this context, we had to consider some of the challenges posed by UVM deployment. First off, the filters have a relatively small footprint in a typical chip to justify the initial bring-up of a full-fledged UVM environment. A typical IoT chip can have more than 10 DSP blocks, and each block will need a separate bench for unit-level verification. Designing math-intensive scoreboards will be laborious and error-prone. Alternately, one will have to invoke the MATLAB model externally and post-process the data. Such efforts are easier said than done. Finally, because it's an interdisciplinary field, we also want to collaborate with non-DV engineers at the minimum. They should be able to change the testbench knobs without UVM knowledge. On the bright side, though, DSP filters have many shared characteristics from a verification perspective. The input and output ports typically have IQ data signals in fixed point format. The data is processed usually in stream or block mode in a simple protocol. The control logic is simple and uniform. The input patterns like impulse, step, and ramp can be reused across many filters. DSP test benches lend themselves well to automated generation and templating.
Hello, I'm Eric Cigan. I'm part of the team at MathWorks responsible for FPGA and ASIC verification tools. I wanted to take a moment to highlight some of the related work in this area. As far back as 2012, Metagraphics introduced what's now known as the UVM framework, or UVMF. UVMF is an open source package. It provides users with reusable UVM methodology and a code generator for test bench generation. Over the years, Metagraphics, now Siemens EDA, integrated UVMF with various high-level design tools. For instance, several years ago, UVMF was integrated with MATLAB through the MATLAB Engine API. This integration enabled the use of MATLAB to develop predictors, checkers, and other test bench components with Questa System Verilog DPI or VHDL FLI. About 6 years ago, MathWorks introduced its own capability to generate System Verilog DPI verification components from either MATLAB or Simulink. Now, both MATLAB and Simulink are used by system designers and algorithm developers to model algorithms, with MATLAB being favored in applications like signal processing and Simulink being favored in controls and analog mixed signal applications. This DPI generation capability produces a shared library and a directory structure that helps engineers incorporate generated verification components into test benches, supporting the leading HDL simulators in use today. Some of the work that we'll cover in the next section was done using this capability. It's also worth noting that Metagraphics updated UVMF several years ago so that it could incorporate these auto-generated System Verilog components for MATLAB and Simulink into the Siemens Questa simulator, though that was not used in the work discussed here today. So Silicon Labs and their work really employed three different approaches we're going to talk about here today. In the first, Silicon Labs developed their own semi-automated solution that relied on the product MATLAB compiler to produce MEX functions. They then used these MEX functions in combination with the library DPI calls, as well as a System Verilog package file with a set of functions that call the DPI functions. So this approach enabled use of MATLAB to create various forms of stimulus using MATLAB's various mathematical operations. Also, because the MATLAB compiler is quite permissive in terms of its MATLAB coding style it supports, nearly any MATLAB code could be used. Now, as Avi will explain in the next few slides, this method involved a lot of programming, and its complexity did make debugging more difficult. Avi will go on to explain the second approach used, in which Silicon Labs created a parameterized verification component, as well as a scripting framework to automatically generate the test bench. This method was also effective, but posed maintenance challenges as well. Avi then worked with Mark Lin from MathWorks, we'll talk a little bit later, to develop a third approach based on the automated System Verilog DPI generation capability for MathWorks I discussed in the last slide. Mark will present several slides illustrating the use of two functions in the MATLAB environment, DPI gen and UVM build, to provide an automated capability that would address the maintainability issues of the first two approaches. Over to you, Avi.
In our first iteration, we started with a MATLAB reference model and used MATLAB compiler to convert it into a C-based Linux shared object file. We then built a DPI layer that could be called from an UVM environment at the start of test. Let's take a look at this flow in more detail. The MATLAB layer has two components, the sample generator and the IP reference model. The sample generator is our stimulus source. It takes variables like testbench seed, pattern type, and number of samples as input and produces the intended stimulus for us. Creating stimulus in MATLAB layer was very convenient. MATLAB comes with a wider array of DSP functions compared to System Verilog. At the same time, we were able to control the stimulus with same SV seed we used in rest of the test bench. The reference model, of course, came straight from the systems team. For the DPI layer, we needed a library of DPI calls to interact with MATLAB functions. The DPI implementation is in C, but it makes use of MEX functions. MEX functions or MATLAB executable functions refer to programs that are automatically loaded and can be called like any MATLAB functions. Using C MEX file applications, we can write C programs that can be called from the MATLAB command line. Some of the DPI functions handle MATLAB bookkeeping activities like initializing and terminating the tool and setting up the libraries. A separate DPI function is needed to invoke the sample generator and the reference model. We also have to do low-level memory management operations like allocating and clearing of the arrays. At this stage, we also recommend creating an optional C test wrapper that can call all the above functions and display the input and output samples generated. This step is a quick sanity check that ensures our DPI layer is working correctly. Finally, we created an SV package file with APIs to call the DPI functions. All the DPI specific code was included in this package file. The UVM test will call these APIs at the start of simulation. The input data obtained will be used to drive RTL during the runtime, adhering to protocol requirements. The output data array will be sent to the scoreboard to perform pattern matching at end of test. Using this three-part technique, we were able to generate the outputs from any input pattern. We did not have to rewrite the reference model in System Verilog, which was great. However, we found that most of the code, particularly in the DPI layer, was repetitive. The low-level programming is also error-prone. Debuggability was another big concern. When fully operational, we have three tools working in tandem: MATLAB, GCC, and SV Simulator. Sometimes the error message from one tool was getting clobbered up by another. Some files worked well in one layer and not so much in the other. Many failures in such cases were null pointer errors or memory access issues. We had limited visibility, no ability to breakpoint through the code. We'll get back to some of these issues shortly. Now that we have a path to include MATLAB models in our testbench environment, we shifted focus to its UVM deployment. This discussion in this section is geared towards coprocessor type of designs that have high degree of similarity in external interface. A more generic solution is discussed in the next section. Our coprocessor has two modes of operation: an AHP mode, where the I/O samples can be written to or read from the filter as an AHP transaction, a FIFO mode where the data can be exchanged through a simple FIFO protocol. We first developed a generic verification environment that could be easily instantiated and run out of the box with default settings. We created an agent for each interface, an AHP agent, a FIFO agent, and also a bypass agent, which just passed through the incoming data with certain delays. So in theory, we could use the environment in a non-coprocessor environment, although we didn't try it. Next, we deployed the coprocessor environment in a filter test bench. We created a base test that instantiated the coprocessor environment and called some sequences from the library. We created additional tests to stress the design. Of course, we had to go back and make some changes to the verification environment since certain items did not work the way we wanted them to. Once we were happy with all the changes and the design was working as per our expectation, we created a scripting framework to generate all the collaterals outside of the coprocessor environment. We tried to push as many collaterals as possible to the coprocessor environment and left the automation layer light. This was because if we had to change the code in automation layer, testbench generation was going to be costly and inefficient. Some items like scoreboard were tricky. We provided a basic scoreboard in automation layer, and we expect it to be changed or overridden frequently. Some of the considerations we made for the coprocessor verification environment included parameterization of variables whenever possible, even if the current design had fixed verdts. We created a generic coprocessor transaction that higher-level sequences could operate on. We minimized any protocol-specific details in this transaction as much as possible. A translation layer to convert the generic transaction to protocol-specific transactions was added separately. We created two levels of configuration components, a protocol-dependent config object for the agent and a protocol-independent config object for the environment. Finally, common assertions and cover groups were provided as a library that could be automatically included or excluded from each filter test bench. The home-root solutions were great, but posed an abundance of maintenance challenges. Despite our best effort, we had to regenerate TB multiple times, sometimes due to test bench bugs and sometimes due to feature changes. In some cases, we found it convenient to manually update a single test bench instead of changing the scripts and regenerating all the test benches. Obviously, it was a bad idea. There was no easy way to reconcile these manual changes if the same TB needed regeneration down the road. Once we took the manual route, we had to stick to it. All this led us to explore other solutions out there.
Thank you, Avi. My name is Mark Lind, Senior Application Engineer with MathWorks. Here I would like to show the steps we took to generate verification artifacts from both MATLAB code and Simulink model. In general, with MATLAB code, for both the reference model and Simulink sequence, they were applied through HDL Verifier's DPI gen capability to generate C code that were later automatically integrated into the RTL test bench via the DPI interface. With MATLAB, we started with a decimate by 8 CIC MATLAB function. This function also contained another subfunction called toCalc_CIC filter. Then a MATLAB wrapper function, TB_dec8, was created to address any code generation constraints and avoid any modification to the original function. It is this wrapper function that is passed to the DPI gen capability as shown here. Note that what's passed to the DPI gen-arg argument is the data type of the wrapper function argument, not the argument itself. Here, DPI gen understands that the first and only argument to TB_dec8 is of type double, which will result in a type of real in System Verilog. In general, with DPI-C code generation, one must also ensure that 1. The argument type and size does not change throughout the execution of this function. While this is allowed during MATLAB simulation, it is not possible during the DPI-C calls. Second, use persistent keyword to define any variables that is needed to hold state, as by default, generate DPI-C code is memoryless. From DPI gen, we get the following 4 functions. The initialization functions, that is responsible for setting up any memory space variables as required by the DPI-C function. The reset function, to be called during hardware reset assert, and the behavior itself. The timing of the behavior is purely controlled by the calling test bench. Whether it is 12 megahertz, 16 megahertz, it is all dependent on how the test bench is called. Then an optional terminate function, which is the reverse of the initialization function that cleans up any kind of memory that was allocated and destroy any variables that is created during the process. As part of the DPI code generation process, a System Verilog module is generated with the DPI-C function already integrated. Here we see that in the initialization block is where we call the DPI-C initialize. In the final block is where we call the DPI terminate. In the always block, where time is determined, we call the reset function when the hardware reset is asserted, and the behavior itself when the positive clock edge is taken away. Now, coming from MATLAB, there is no direct path to UVM code generation. Each generated DPI function must be manually integrated into the existing UVM environment. For UVM code generation, we must use Simulink. Similar to MATLAB and DPIC, we apply our Simulink model through the HDL verifier, but this time we call UVM build instead. And what we get is a complete test case with any DPIC functions automatically integrated. UVM generation process is relatively simple. As shown here, the structure of Simulink model must resemble that of a UVM testbench architecture. MATLAB functions such as tb_dec8 was pulled in via the MATLAB function block. tb_dec8 was used instead of the original CIC code because DPIC code generation constraints mentioned earlier also apply here, as DPIC capability is used heavily in the generation of the UVM testbench. UVM build only requires the Simulink path to components such as the sequence, scoreboard, predictor, etc. Now, to expedite the process and avoid having to type out these paths over and over again, we created a simple script that remembers the path and then pass it on to the UVM build. The results of the UVM build is a UVM test case that we can either run as whole or disseminate and integrate into existing testbench and parts. Each Simulink block results as a UVM component. Each Simulink connections results as a TLM with its corresponding UVM objects. TLM connections between components are then defined by Simulink model connections. All supporting components such as environment, agents are then automatically generated. Here, we see a very standard output from the UVM build. The sequence talks to our standard sequencer. The sequencer drives the driver, which then in turn drives the design under test. The output of the design under test is then monitored by the generated UVM monitor, goes through a TLM FIFO, and the TLM FIFO drives the scoreboard, which is also listening to the predictor that we model, which is also going through the TLM FIFO. Here we show the file list that comes from the generated process. Lastly, the UVM generation process also generates a EDH simulator kickoff script, which in our case is the Siemens QuestaSim, which we simply pass the generated.do files to QuestaSim to execute our simulation.
Thank you, Mark and Avi. Based on the effectiveness of the work in this case study, Silicon Labs intends to go forward with additional work using the automated method discussed by Mark. They will work to incorporate the use of assertions and coverage in this automated workflow. They will investigate use of System C for control of the data path in conjunction with the Simulink model. They want to explore using co-simulation of MATLAB with Questa to run the MATLAB model in lockstep with the RTL. And they want to try using direct generation of RTL from Simulink for use in FPGA prototyping or emulator hardware. For the time being, Silicon Labs has developed a hybrid approach. For existing legacy blocks, they'll use the first approach described here. A key benefit of that approach was that MATLAB compiler didn't impose constraints on MATLAB coding style. For new blocks, though, they will use the DPI gen and UVM build capabilities that Mark covered. It's worth noting that these capabilities do impose some constraints on MATLAB coding style, but their system designers are being familiarized with this from the start. The results obtained using this more automated approach were considerable, with a large increase in the number of tests that could be performed and a reduction in the time that was required to develop test benches, down from 2 to 3 weeks to less than 2 days. Finally, this method gives system designers the ability to modify test benches on their own without pulling in hardware designers or verification engineers, resulting in more of a collaborative workflow. Now, this page lists some additional resources for anyone interested in for further information, in particular about the use of DPI gen and UVM build functions that were used to automate generation of test bench components from MATLAB code or Simulink models. We also have links to examples here and the product pages. Thank you very much.